Stephen Hawking's groundbreaking contribution to cosmology reshaped our understanding of the universe's origins. Before his work, scientists and philosophers had been struggling for centuries to answer the most fundamental question of all: how did the universe begin? The earliest models of the cosmos often placed the universe in a timeless, static state. It was not until the 20th century that a more dynamic and scientific understanding began to emerge. Albert Einstein's theory of general relativity, in particular, revolutionized the way we viewed space and time, showing that both were intertwined in a fabric known as spacetime. But even with this new understanding, the origins of the universe remained a mystery. The classic view, based on the Big Bang theory, suggested that the universe began as a singularity, a point of infinite density and temperature. This model proposed that at some point, roughly 13.8 billion years ago, all of the universe's matter and energy was concentrated in a tiny, infinitely dense point. The Big Bang then represented the moment when this singularity expanded rapidly, giving rise to the universe as we know it. But this idea, while powerful, came with a set of unresolved issues, particularly surrounding the nature of time itself. What came before the Big Bang? Could the concept of before even apply in this context? These questions remained unanswered, leading many to speculate that time itself must have had a starting point, much like the universe. However, Stephen Hawking would challenge this conventional wisdom. In the 1,960 seconds, while working on his doctoral thesis, Hawking began to explore these questions in earnest. His work built on the foundation laid by earlier cosmologists, including George Lemaitre and Edwin Hubble. Lemaitre's discovery of the expanding universe and Hubble's observations of distant galaxies showed that the universe was not static, but was constantly expanding. This led to the realization that the universe had a beginning, an event known as the Big Bang. But while the idea of the Big Bang was revolutionary, it did not explain the deeper question of the origin of the universe itself. The notion that the universe began from a singularity, a point of infinite density, was problematic because it implied that the laws of physics themselves broke down at this point. This presented a paradox. How could the universe come from a singularity where the conventional laws of physics did not apply? Hawking's breakthrough came when he applied the mathematics of general relativity to these questions in a novel way. By combining general relativity with the emerging theory of quantum mechanics, he sought to develop a more complete understanding of the early universe. The foundation of his work rested on a key insight. The laws of physics must be applied in a way that accounted for both the behavior of large-scale cosmic phenomena, governed by general relativity, and the behavior of microscopic particles, governed by quantum mechanics. Quantum mechanics, with its probabilistic nature, had long been seen as incompatible with general relativity, which is deterministic. However, Hawking's brilliance lay in his ability to merge these two distinct areas of physics into a unified framework. In the early 1970 seconds, Hawking, in collaboration with his colleague Roger Penrose, developed a set of equations that describe the behavior of spacetime near the Big Bang. These equations, known as the Penrose-Hawking singularity theorems, showed that under certain conditions, the universe must have had a beginning. The key breakthrough in Hawking's work was the realization that this beginning was not a singularity, as previously thought, but rather a boundary of spacetime that could be understood using quantum mechanics. Instead of the universe emerging from an infinitely dense point, as the singularity model suggested, Hawking proposed that the universe emerged from a state where the concept of time itself no longer applied in the way we understand it. At the heart of this idea was the concept of imaginary time. Hawking's work suggested that time, in the context of the very early universe, could be modeled as a dimension of space, a concept that was foreign to the classical view of time as a linear progression. Imaginary time, a concept borrowed from mathematics, allowed for the possibility that the universe did not have a specific beginning in the conventional sense. Instead, time could be viewed as part of a broader, timeless structure in which the boundaries of time and space were fluid, without a distinct start or end. This radical departure from the conventional Big Bang model was a game-changer in the field of cosmology. Hawking's ideas opened up new possibilities for understanding the birth of the universe, allowing scientists to explore the origins of space and time without the need for a singular starting point. This work fundamentally shifted the way we think about the universe's past and its future. It also raised important philosophical questions about the nature of time itself. If time had no beginning, then how should we understand the idea of causality? If the universe did not have a definitive origin, what did that say about our place in it? For many years, cosmologists had been trapped in a debate between two competing views of the universe. The classical view, based on Newtonian physics, depicted the universe as a clockwork mechanism that operated according to precise and predictable laws. On the other hand, the quantum mechanical view suggested that the universe was inherently probabilistic and unpredictable. Hawking's contribution was to bridge this gap, providing a theoretical framework that allowed both perspectives to coexist. He proposed that the early universe, at the quantum level, could be described by a wave function, a mathematical expression that encapsulated the probabilities of different outcomes, in the same way that quantum mechanics describes the behavior of subatomic particles. In this view, the universe did not have a single, deterministic history, but rather a range of possible histories, each of which could evolve into the universe we see today. This idea was revolutionary because it suggested that the universe's evolution was not predetermined, but rather governed by the interplay of quantum probabilities. Rather than a singular beginning point, the universe's creation could be described as a quantum event, a process that unfolded according to the principles of quantum mechanics, which govern the behavior of all matter and energy at the smallest scales. For Hawking, this was the key to understanding the origin of the universe. The universe was not born from a singular point of infinite density, but from a quantum event that unfolded in a probabilistic manner. The implications of Hawking's work were far-reaching. By proposing a quantum mechanical description of the universe's birth, he opened the door to new ways of thinking about the early universe. His work laid the groundwork for future research in cosmology, leading to new discoveries and theories about the nature of black holes, the expansion of the universe, and the fundamental forces that govern the cosmos. But perhaps his most profound contribution was the way he made cosmology accessible to the public. Through his best-selling book, A Brief History of Time, Hawking brought the complex ideas of theoretical physics into the mainstream, making them understandable to a broad audience. His ability to communicate his groundbreaking ideas to the public helped elevate cosmology from a niche academic discipline to a subject of global interest. At the same time, Hawking's work challenged the scientific community to rethink some of the most fundamental assumptions about the universe. His ideas about imaginary time, for example, questioned the very nature of time itself, forcing scientists to reconsider the ways in which time might be understood in the context of cosmology. His work also raised important questions about the role of the observer in the universe. If the universe's origins could be described in terms of quantum probabilities, then what role did the observer play in shaping the universe's history? These questions would continue to fuel debates in cosmology for years to come, and they remain central to the field today. Hawking's contribution to cosmology cannot be overstated. His work fundamentally changed our understanding of the universe's origin, providing a new theoretical framework for thinking about time, space, and the nature of reality itself. By challenging conventional views and introducing the concept of imaginary time, Hawking opened up new possibilities for understanding the beginning of the universe and, by extension, our place in it. His work has left an indelible mark on the field of cosmology and will continue to inspire future generations of scientists and thinkers as they seek to answer the most profound questions about the nature of the cosmos. In many ways, Stephen Hawking's work marked the beginning of a new era in cosmology. By merging the insights of quantum mechanics with the theory of general relativity, he was able to offer a more complete and unified understanding of the universe's origins. And in doing so, he rewrote the very beginning of time itself. As we continue to explore the depths of Stephen Hawking's revolutionary ideas, it becomes clear that his contributions not only altered the course of cosmology, but also reshaped the way we perceive the universe itself. Hawking's work was more than just a scientific breakthrough. It represented a new philosophical outlook on the very nature of existence. It pushed the boundaries of human knowledge, compelling us to reconsider the very foundation upon which our understanding of time, space, and the universe rests. The key to understanding Hawking's contribution lies in his novel approach to the Big Bang theory. While the standard model of the Big Bang had long been established as the leading explanation for the universe's origins, it was based on an understanding that time itself began at the moment of the Big Bang. This view, however, left many questions unanswered. If time began at the Big Bang, what was there before it? Could the universe have existed in some form before the Big Bang, and if so, what would the nature of time have been in that context? These questions were fundamental, and the fact that they were left unaddressed made the Big Bang theory incomplete in the eyes of many. In his search for answers, Stephen Hawking confronted this problem head-on. His work on the nature of time led him to a radical rethinking of the very structure of the cosmos. The standard view of the universe suggested that time had a beginning, and that this beginning was linked to the event known as the Big Bang. But Hawking's theory of imaginary time challenged this conventional understanding. Imaginary time, as introduced by Hawking, was not a simple extension of real time, but rather a separate dimension altogether. It was a concept drawn from complex numbers in mathematics, a field that describes numbers in two dimensions, one real and the other imaginary. In simple terms, while real time moves forward in a straight line from past to present to future, imaginary time takes a different path. It can be thought of as a mathematical construct that allows for the possibility of time having no clear beginning or end. Imaginary time does not follow the conventional rules of causality that govern real time. Instead, it behaves more like a spatial dimension in which the universe could have emerged smoothly without a sharp beginning at the moment of the Big Bang. According to this model, the universe could be described by a closed, finite geometry without any singular starting point. One of the most significant aspects of Hawking's work was the way he used the concept of imaginary time to eliminate the need for a singularity at the beginning of the universe. In the standard Big Bang model, the universe began as a point of infinite density, what is known as a singularity. However, this idea posed several problems. For one, it was impossible to describe the physics at such a point because the laws of physics themselves broke down at this singularity. Furthermore, the concept of a singularity suggested that time itself had a definite start, raising the question of what happened before this moment. Hawking's solution to these problems was the idea that the Big Bang was not a singularity, but rather a smooth, boundaryless event that could be described in terms of imaginary time. In this model, the universe's beginning was not marked by a sudden explosion from an infinitely dense point, but by a smooth transition from imaginary time to real time. Time itself, in this view, could be thought of as a continuous dimension that does not have a starting point or an end point. Instead of a universe that began in the traditional sense, Hawking proposed that the universe simply emerged from a timeless, boundaryless state. This radical shift in thinking about the beginning of the universe had far-reaching implications. It not only resolved the problem of the singularity at the heart of the Big Bang theory, but it also allowed for a new way of thinking about the nature of time itself. In Hawking's model, time was no longer a linear progression that had a clear starting point. Instead, it was part of a broader, more fluid structure in which the concept of a beginning or end became less important. This new understanding of time opened up exciting new avenues for exploring the universe's origins, as well as its ultimate fate. Hawking's work also incorporated one of the most fundamental principles of quantum mechanics, the idea that the universe is governed by probabilities rather than deterministic laws. In traditional physics, the laws of motion are deterministic, meaning that given the state of a system at one time, its future can be predicted with absolute certainty. However, in the realm of quantum mechanics, events are probabilistic, meaning that we can only predict the likelihood of different outcomes, not the exact outcome itself. Hawking recognized that the behavior of the early universe could not be described by classical physics alone. Instead, it required a quantum mechanical framework. In this framework, the universe was not a deterministic system with a clear, predictable history. Instead, it was a probabilistic system in which multiple potential histories could emerge, each one governed by the laws of quantum mechanics. This view of the universe as a quantum event rather than a deterministic process was one of Hawking's most profound contributions. In order to describe this quantum universe, Hawking introduced the concept of the wave function of the universe. This wave function was a mathematical expression that described all possible states of the universe, much in the same way that quantum mechanics describes the probabilities of different outcomes for subatomic particles. The wave function of the universe did not describe a single, deterministic history of the cosmos, but rather a range of possible histories, each one having a different probability of occurring. This concept of the wave function of the universe had profound implications for our understanding of the universe's origins. It suggested that the universe did not have a singular, deterministic beginning, but instead could have arisen from a range of possible scenarios, each one influenced by quantum probabilities. In this view, the early universe was not a fixed, unchanging state, but a dynamic, evolving system governed by quantum laws. One of the most interesting aspects of Hawking's work was its ability to reconcile the seemingly contradictory views of the universe offered by general relativity and quantum mechanics. For much of the 20th century, physicists struggled with the fact that these two theories, while both successful in their own domains, appeared to be fundamentally incompatible. General relativity described the large-scale structure of the universe, including gravity, while quantum mechanics explained the behavior of subatomic particles. However, the two theories operated under different sets of rules and assumptions, making it difficult to combine them into a unified theory of everything. Hawking's work on the early universe helped to bridge this gap. By using the mathematical tools of both general relativity and quantum mechanics, he was able to develop a new framework for understanding the universe's origins. His work demonstrated that the universe could be described in terms of both the smooth, continuous structure of spacetime and the probabilistic, uncertain behavior of quantum particles. In doing so, he showed that the universe's birth could be understood as a quantum event that unfolded in a way that was consistent with both general relativity and quantum mechanics. Hawking's theory also had important implications for our understanding of black holes. His work on the nature of singularities, which were previously thought to be the ultimate end of time and space, showed that these singularities could be described in terms of quantum mechanics. This led to the development of his famous theory of black hole radiation, known as Hawking radiation. According to this theory, black holes are not completely black, but emit radiation due to quantum effects near the event horizon. This discovery revolutionized our understanding of black holes and has had lasting implications for the field of theoretical physics. Beyond his scientific contributions, Stephen Hawking's ability to communicate his ideas to the public also played a crucial role in the popularization of cosmology. His book, A Brief History of Time, became a global bestseller and introduced millions of readers to the complex concepts of modern physics. Through his writing and public appearances, Hawking made abstract scientific ideas accessible to a broad audience, inspiring a new generation of scientists, philosophers, and curious minds to explore the mysteries of the universe. Hawking's work continues to shape our understanding of the universe today. His theories have been the subject of countless studies, debates, and further developments. Even as new discoveries and technologies push the boundaries of our knowledge, the core ideas Hawking developed remain fundamental to the field of cosmology. His legacy is not just in the theories he proposed, but also in the way he redefined the questions we ask about the universe and the tools we use to explore them. Stephen Hawking's groundbreaking contributions to cosmology, particularly his theory of the origin of the universe, have left an indelible mark on the scientific world and have reshaped the way we view our place in the cosmos. In the end, Stephen Hawking's vision of the universe as a quantum event without a distinct beginning or end opens up an entirely new way of thinking about the cosmos. His groundbreaking work has not only provided us with new theoretical tools for understanding the universe's birth, but has also challenged us to reconsider the very nature of time and existence. Through his work, Stephen Hawking rewrote the beginning of time and set the stage for future generations of scientists to continue the exploration of the universe's most profound mysteries. In the world of cosmology, there are few figures as influential and revered as Stephen Hawking. His work not only advanced our understanding of the universe, but also fundamentally altered the way we think about the nature of time and space itself. To understand the revolutionary nature of Hawking's contributions, it is essential to explore the historical context in which his work emerged. During the 20th century, cosmology underwent a transformation. The ideas that dominated the field before Hawking's time were based on classical physics, which provided a solid but limited understanding of the universe. However, Hawking's research would challenge these existing theories, providing a more nuanced, complex, and unified model that bridged the gap between two powerful, yet seemingly incompatible, theories: general relativity and quantum mechanics. The birth of modern cosmology was marked by Albert Einstein's development of the theory of general relativity in the early 20th century. This theory revolutionized the understanding of gravity, space, and time. Prior to Einstein, gravity was understood simply as a force between objects with mass, as described by Isaac Newton. However, Einstein's general theory of relativity proposed that gravity was not just a force, but the result of massive objects curving the very fabric of space and time. This new understanding of gravity led to a dramatic shift in how scientists viewed the cosmos. Instead of thinking of space and time as separate entities, Einstein showed that they were interconnected in a four-dimensional fabric known as space-time. This insight laid the foundation for much of the modern understanding of cosmology. In the years following Einstein's revolutionary work, a number of new discoveries and theories emerged that further changed the landscape of cosmology. One of the most important developments came in the 1920 seconds with the work of Edwin Hubble, who discovered that the universe was expanding. By studying the light emitted by distant galaxies, Hubble found that galaxies were moving away from each other, a phenomenon now known as the redshift. This observation was a clear indication that the universe was not static but rather expanding over time. The idea that the universe had a beginning gained traction, and the prevailing theory became that the universe had originated from a single, infinitely dense point, known as the Singularity, which later expanded in what we now call the Big Bang. At this point, the Big Bang theory became the dominant model for the origin of the universe. The theory was initially proposed by Georges Lemaitre in the 1922, who suggested that the universe had begun as a cosmic egg and had been expanding ever since. This idea was further developed in the 1940 and 1950, gaining more widespread acceptance as more evidence supporting the expansion of the universe was found. By the 1960s, the Big Bang theory was largely embraced by the scientific community, and the search for evidence of the universe's origins became a central goal of cosmologists. However, despite the widespread acceptance of the Big Bang theory, there were significant unanswered questions. The most pressing question was the nature of the very beginning of the universe. According to the Big Bang model, the universe originated from an in-question POC, infinitely dense point, a singularity, but this concept posed significant problems. At the singularity, the laws of physics, as we know them, break down. There is no way to describe the physical state of the universe under such extreme conditions, and as a result, the very idea of a singularity became problematic. If the universe began as a singularity, what happened before that moment? Could the laws of physics still apply at this point, or did time and space even exist before the Big Bang? These questions created a significant gap in the theory of the Big Bang, and the scientific community was divided over how to address them. Some cosmologists argued that time itself began at the Big Bang, and thus the question of what happened before was meaningless. In this view, the universe had no past, and the Big Bang marked the beginning of both space and time. However, this idea raised its own set of problems, as it suggested that the universe could have arisen from nothing, which seemed impossible according to the principles of physics. It was against this backdrop of uncertainty and unresolved questions that Stephen Hawking began his work on the origin of the universe. Hawking was not the first to grapple with the problem of the universe's beginning, but he would go on to provide a solution that would not only answer some of the most fundamental questions of cosmology, but also challenge many of the accepted ideas of his time. His research would build on the foundations laid by Einstein and others, but it would also introduce new ways of thinking about space, time, and the universe. Hawking's breakthrough came in the 1970s when he began to work on the problem of black holes. Black holes had been predicted by Einstein's theory of general relativity, but they remained a theoretical curiosity for many years. It was not until the 1960s that scientists began to seriously consider their existence, and in the 1970s, Hawking made a remarkable discovery that changed the way scientists thought about black holes and their connection to the universe's origin. Hawking showed that black holes were not entirely black, but emitted radiation due to quantum effects near the event horizon. This radiation, now known as Hawking radiation, was a revolutionary idea because it suggested that black holes could eventually evaporate over time, challenging the previously held belief that nothing, not even light, could escape a black hole. Hawking's work on black holes was closely linked to his work on the beginning of the universe. Both required a deep understanding of general relativity and quantum mechanics, two areas of physics that, for much of the 20th century, had been thought to be incompatible. General relativity described the large-scale structure of the universe, including the force of gravity, while quantum mechanics described the behavior of particles at the smallest scales. The challenge for Hawking was to find a way to reconcile these two theories in a way that would make sense of the universe's origins. Hawking's solution was to apply the principles of quantum mechanics to the very early universe at the moment of the Big Bang. He used quantum theory to describe the behavior of space-time itself, proposing that the universe did not originate from a singularity, but from a smooth, boundaryless state. This idea was based on the concept of imaginary time, a mathematical construct that Hawking used to describe the universe's beginning. According to Hawking's model, time itself was not a linear progression, but rather a dimension of space that could be described mathematically as part of a broader, timeless structure. This allowed Hawking to eliminate the singularity at the heart of the Big Bang model and suggest that the universe could have originated in a smooth, continuous manner rather than from an infinitely dense point. Hawking's model of the universe's origin was groundbreaking because it challenged the conventional view that time had a clear starting point. By introducing the concept of imaginary time, he showed that the universe's beginning could be understood without the need for a singularity. Instead of a sharp, defined beginning, Hawking proposed that the universe emerged from a smooth, boundaryless state, a view that reconciled the laws of general relativity with the principles of quantum mechanics. This marked a dramatic departure from the classical view of the Big Bang and provided a new framework for understanding the cosmos. Hawking's work not only changed the way we think about the universe's origins, but also had profound philosophical implications. If the universe had no beginning in the traditional sense, then what did this mean for our understanding of time itself? Could the universe have existed forever, or was it part of an eternal cycle of birth and rebirth? These questions were not easily answered, and they led to new debates within the scientific community about the sacred nature of time and the universe. Some scientists embraced Hawking's ideas as a profound breakthrough, while others were more cautious, unsure about the implications of a universe without a clear beginning. Hawking's work also posed new questions about the nature of causality. If time had no beginning, then how should we think about cause and effect? In the classical view of the Big Bang, causality was clear. The Big Bang caused the universe to expand, and everything that followed was a consequence of that event. However, in Hawking's model, causality was no longer a simple, linear progression. Instead, the universe could be thought of as a quantum event governed by probabilistic laws, rather than a deterministic system. This raised important philosophical and scientific questions about the role of the observer in the universe and the nature of causality itself. The historical context of Hawking's work is crucial for understanding the radical nature of his ideas. Before Hawking, the prevailing view of the universe's origin was based on the Big Bang theory, which suggested that the universe began as a singularity. This model raised significant problems, particularly concerning the nature of time and the breakdown of the laws of physics at the singularity. Hawking's work on the nature of time and the origin of the universe challenged these assumptions and provided a new framework for understanding the cosmos. His theory of imaginary time and his work on quantum mechanics fundamentally changed the way we think about the universe, offering a more unified and comprehensive understanding of its origins. In the end, Stephen Hawking's work on the Big Bang and the origin of the universe represented a profound shift in our understanding of cosmology. It bridged the gap between general relativity and quantum mechanics, offering a new perspective on time, space, and the very beginning of the cosmos. His work challenged the conventional view of the Big Bang and provided a new theoretical framework for understanding the universe's origins. In doing so, Hawking not only revolutionized cosmology, but also reshaped the way we think about the nature of reality itself. Hawking's work, particularly his introduction of the concept of imaginary time and his reconciliation of quantum mechanics with general relativity, was nothing short of revolutionary. His ability to merge these two distinct yet powerful frameworks allowed him to present a new model of the universe's origin. But to fully appreciate how groundbreaking his work was, it's important to understand the landscape of scientific thought before Hawking's contributions and how his ideas directly challenged the prevailing theories of the time. At the core of the classical Big Bang model was the idea that the universe began from an infinitely small, infinitely dense point referred to as the singularity. This singularity was not just a theoretical curiosity, but a central tenet of the Big Bang theory. Scientists had long grappled with the implications of this model, but it posed several problems, the most glaring of which was that it appeared to be a breakdown in the very laws of physics. The singularity described a point at which the laws governing space-time and matter no longer held, making it impossible to describe or understand the conditions that existed at that moment. In the early 1970s, Hawking, in collaboration with Roger Penrose, began to explore these issues through their work on the structure of space-time near black holes. They developed the Penrose-Hawking singularity theorems, which showed that under the right conditions, singularities were not just theoretical curiosities, but a fundamental feature of the universe. These theorems demonstrated that the Big Bang must have been a singularity, an infinitely small point at the beginning of time. While this work was groundbreaking in its own right, it also highlighted the limitations of the Big Bang model. The existence of a singularity at the heart of the universe's origin suggested that the laws of physics could not apply at this point, raising serious questions about the consistency and completeness of the Big Bang theory. Hawking's most significant contribution was his shift away from the concept of a singularity. While many of his contemporaries accepted the idea of a singularity as the natural endpoint of general relativity, Hawking recognized that the laws of physics could not be applied to such a point. In his view, a true understanding of the universe's origins could not come from a theory that broke down at the very moment the universe came into existence. This led him to propose a new framework that integrated both general relativity and quantum mechanics, providing a more comprehensive picture of the universe's birth. The introduction of imaginary time was perhaps the most radical aspect of Hawking's model. In the classical view of the Big Bang, time was seen as a linear progression. There was a clear beginning at the moment of the Big Bang, and everything that followed could be traced back to this point in time. However, Hawking's use of imaginary time allowed him to view time not as a simple linear progression, but as a dimension of space. In this view, time could be treated mathematically as part of a broader, unified structure that did not have a distinct beginning or end. By treating time as imaginary, Hawking effectively eliminated the singularity at the heart of the Big Bang. Rather than a universe emerging from a point of infinite density, he proposed a model in which the universe emerged smoothly from a boundaryless state. This allowed for a more complete description of the universe's origin, one that avoided the contradictions and paradoxes of the classical model. In this new framework, the universe did not have a specific starting point. Instead, it could be understood as having a continuous, infinite existence that had no beginning or end. This radical departure from the conventional Big Bang model posed a direct challenge to the prevailing view of the universe's origins and provided a more consistent and unified explanation. Hawking's work was not just a theoretical exercise, it had profound implications for the field of cosmology and the way scientists viewed the universe. Before Hawking, the Big Bang was understood as a singular event that marked the birth of the universe, with time itself beginning at that moment. The singularity at the center of this event created a boundary beyond which the laws of physics could not be applied. This view was limited, as it left unanswered questions about the nature of time and the possibility of a universe that existed before the Big Bang. By proposing a model in which the universe had no boundaries and time was viewed as a smooth, continuous dimension, Hawking opened up new possibilities for understanding the universe's origins. In many ways, Hawking's work on the nature of time and the origin of the universe represented a shift from classical thinking to a more modern, quantum mechanical understanding of the cosmos. Quantum mechanics, with its probabilistic nature, had long been seen as incompatible with general relativity, which is deterministic in nature. The two theories operated under different assumptions and were thought to describe different aspects of reality, one describing the behavior of the very large gravity and space-time, and the other describing the behavior of the very small particles and quantum fields. Hawking's ability to bridge the gap between these two frameworks allowed him to develop a more unified model of the universe, one that incorporated both the smooth, continuous nature of space-time and the probabilistic, uncertain behavior of quantum events. This integration of quantum mechanics and general relativity was one of the key features of Hawking's work. He recognized that the early universe was governed by both quantum principles and the effects of general relativity. By combining these two perspectives, he was able to propose a new way of understanding the universe's origins. His work showed that the universe could be described as a quantum event, a process that unfolded in a probabilistic manner, governed by the laws of quantum mechanics, rather than a deterministic process. In doing so, Hawking's model moved beyond the constraints of classical cosmology, providing a more complete and unified understanding of the universe's birth. By using quantum mechanics to describe the early universe, Hawking was able to explain the emergence of space-time itself, bridging the gap between the quantum and the classical. This allowed him to propose a more coherent picture of the universe's origin, one that did not rely on the concept of a singularity or a distinct starting point. Instead, the universe could be seen as part of an eternal, continuous process that had no boundaries or clear beginning. Hawking's work also had profound implications for the future of cosmology. His ideas on imaginary time and the wave function of the universe sparked new debates and research into the nature of time, space, and the universe's ultimate fate. One of the key questions raised by his work was the nature of the multiverse, the idea that our universe may be just one of many universes that exist in a larger, multiversal framework. If the universe did not have a specific beginning and was governed by probabilistic laws, then it is possible that other universes with different physical properties and laws could exist. This idea has become one of the most exciting areas of research in modern cosmology, and has led to new theories and models of the universe's structure and evolution. The historical context of Hawking's work is crucial for understanding the magnitude of his contributions. Before Hawking, the prevailing view of the universe's origins was rooted in classical physics, with a focus on determinism and the concept of a singular starting point. The introduction of quantum mechanics to cosmology had already begun to challenge these ideas, but Hawking's work provided the missing piece that connected these two seemingly incompatible theories. By introducing imaginary time and describing the universe as a quantum event, Hawking was able to propose a new framework that explained the universe's origin in a way that was consistent with both general relativity and quantum mechanics. This shift in thinking about the origin of the universe had far-reaching implications, not just for cosmology, but for the way we think about time, causality, and the very nature of reality itself. Hawking's work challenged the very foundations of classical thinking, opening up new possibilities for understanding the universe and our place within it. His ability to reconcile the probabilistic nature of quantum mechanics with the smooth, continuous structure of space-time was a monumental achievement, one that has shaped the course of cosmological research for decades. Stephen Hawking's work on the origin of the universe and his challenge to existing theories of the Big Bang remains one of the most important contributions to modern physics. His ability to think beyond the constraints of classical cosmology and introduce new ideas, such as imaginary time and the wave function of the universe, has changed the way scientists approach the deepest questions about the cosmos. By bridging the gap between quantum mechanics and general relativity, Hawking provided a unified framework for understanding the universe's origins, one that continues to shape cosmological research today. His work remains a testament to the power of human curiosity and the endless quest to understand the mysteries of the universe. Stephen Hawking's groundbreaking contributions to cosmology revolutionized the way we think about the universe's origins. One of his most radical and profound ideas was his proposal that the universe has no boundaries. This concept, which came to be known as the no-boundary condition, challenged conventional understandings of space, time, and the nature of the universe itself. Before Hawking, the prevailing view of the universe was shaped by the idea that the universe had a beginning and, by extension, a boundary, a point where the laws of physics, as we know them, ceased to function. Hawking, however, proposed something far more radical, that the universe, in its earliest moments, could have no boundaries, and that it could be fully described by the principles of quantum mechanics. Hawking's no-boundary condition was not just a theoretical curiosity, but a rethinking of the very structure of the cosmos. It offered a new way of understanding how the universe began, how it evolved, and what it means for the concept of time itself. The idea that the universe had no boundaries was a profound challenge to the existing Big Bang model, which had been the dominant theory for explaining the origins of the universe for decades. According to the Big Bang theory, the universe began as an infinitely dense point, a singularity from which it expanded, and time itself began at this point. This theory left unanswered questions about what happened before the Big Bang and whether the concept of time as we know it even applied before that moment. The no-boundary condition that Hawking proposed was built on the mathematical framework of quantum mechanics and general relativity. While general relativity had long been used to describe the large-scale structure of the universe, quantum mechanics, which governed the behavior of particles at the smallest scales, was not easily reconciled with general relativity. However, Hawking's work sought to bridge these two fundamental areas of physics. By combining the insights of both quantum mechanics and general relativity, he developed a model of the universe in which the Big Bang was not the origin of time, but the beginning of a smooth, boundaryless universe governed by quantum laws. This radical idea was first introduced in the early 1982 when Hawking, in collaboration with his colleague James Hartle, proposed a new model for the beginning of the universe. The model was based on a concept borrowed from the field of mathematics, the idea of imaginary time. Imaginary time is a mathematical construct used to describe certain types of quantum systems, and it allows for the possibility that time may not always behave as we experience it. In the context of the early universe, imaginary time allowed Hawking to describe the beginning of the universe in such a way that it did not require a singularity, a point of infinite density, or a boundary. In this framework, the universe could be thought of as having no beginning or end, but rather as existing within a continuous, self-contained loop of space and time. The concept of imaginary time provided a way to avoid the problem of a singularity at the Big Bang, and it also eliminated the need for a before the Big Bang, because time itself was redefined. Time, in this view, could be treated as a dimension similar to space, a dimension that could be smoothly curved and finite, but without a distinct beginning or end. This model eliminated the need for a boundary in both time and space, offering a new way of thinking about the universe that was consistent with the principles of quantum mechanics and general relativity. The implications of this concept were enormous. The idea that the universe had no boundaries fundamentally challenged the traditional notion of the Big Bang. In the traditional view, the universe emerged from an infinitely dense point in time, and that moment marked the beginning of both the universe and time itself. The idea of a boundaryless universe, in contrast, suggested that the universe could have always existed in some form without a distinct beginning or end. Hawking's no-boundary model painted a picture of a universe that was self-contained and finite, but without any sharp boundaries or edges. Instead of a universe that began from a singularity, the universe could be seen as having emerged smoothly from a quantum state, governed by the laws of quantum mechanics. Hawking's model of the universe's beginning was also revolutionary in its rejection of determinism. The classical view of the universe was deterministic. If we knew the state of a system at one time, we could predict its future with certainty. However, quantum mechanics, the theory that governs the behavior of subatomic particles, is fundamentally probabilistic. In quantum mechanics, the future is not predetermined but governed by probabilities. Hawking's proposal of a boundaryless universe incorporated this probabilistic view of reality. In his model, the universe's origin could be understood not as a deterministic event, but as a probabilistic event, a quantum fluctuation that could unfold in a variety of ways, with each possibility governed by the laws of quantum mechanics. This shift from a deterministic to a probabilistic view of the universe's origins was a major departure from the classical cosmology of the early 20th century. Before Hawking, cosmologists had assumed that the universe had a clear, singular beginning, a point at which the laws of physics were fully understood. Hawking's model, by contrast, proposed that the universe's beginning was not a single, well-defined event, but a quantum phenomenon with multiple possibilities. This view fit better with the principles of quantum mechanics, where the universe was not an ordered machine but a probabilistic system with a range of potential outcomes. The no-boundary condition also had profound implications for the nature of time itself. In traditional models of the universe, time was viewed as a linear progression, a continuous flow from the past, through the present, and into the future. The Big Bang theory held that time itself began at the moment of the Big Bang and has been unfolding ever since. In Hawking's model, time was viewed as a finite, continuous dimension that was part of a broader, boundaryless structure. In this view, time did not have a distinct beginning, and the universe did not emerge from nothing. Instead, the universe could be seen as having always existed in some form, with time itself existing as part of a smooth, self-contained fabric of space and time. The philosophical implications of Hawking's no-boundary proposal were profound. For centuries, the question of the origin of the universe had been closely tied to the question of the origin of time. In many religious and philosophical traditions, the beginning of the universe was seen as synonymous with the beginning of time, a moment of creation that marked the start of everything. Hawking's model, by contrast, suggested that the universe could be eternal, without a clear beginning or end. This model posed a direct challenge to the traditional view of creation, suggesting that the universe could be self-contained and independent of any external cause. It also raised questions about the nature of time itself. If time had no beginning, then what was the relationship between time and the universe? And if time had no boundary, then how should we think about the passage of time and the events that unfold within it? Despite the radical nature of Hawking's ideas, the no-boundary condition was not merely a theoretical speculation. Hawking's work had a significant impact on the way cosmologists thought about the structure of the universe and its origins. His ideas provided a framework for understanding the earliest moments of the universe that was consistent with both general relativity and quantum mechanics. They also opened up new avenues for exploring the nature of the universe's creation and the possibility of a self-contained cosmos that did not require an external cause. One of the key components of the no-boundary condition was its ability to resolve the problem of the singularity at the heart of the Big Bang theory. The traditional model of the Big Bang suggested that the universe began from a singularity, a point of infinite density and temperature where the laws of physics broke down. This singularity presented a fundamental problem for cosmologists, as it was impossible to describe the physics at this point. Hawking's model, by contrast, avoided the need for a singularity by proposing a smooth, boundaryless origin for the universe. This allowed scientists to describe the universe's creation without invoking the paradoxes and contradictions that arose from the idea of a singularity. Hawking's work on the no-boundary condition also had a profound impact on the search for a unified theory of physics. For much of the 20th century, physicists had been attempting to reconcile the two great pillars of modern physics: general relativity, which describes the large-scale structure of the universe, and quantum mechanics, which governs the behavior of particles at the smallest scales. Hawking's model of the universe's beginning provided a framework for understanding how these two theories could work together, offering a more unified view of the cosmos that incorporated both the smooth fabric of space-time and the probabilistic nature of quantum mechanics. The no-boundary condition was not just a new way of thinking about the universe's origins, but a paradigm shift that influenced how scientists approached the study of the cosmos. It raised questions about the nature of time, space, and the very fabric of reality. It also opened up new possibilities for understanding the universe as a quantum event, a probabilistic phenomenon that unfolded according to the laws of quantum mechanics. This view of the universe as a self-contained, boundaryless system challenged the classical, deterministic models of the universe and paved the way for new ideas in cosmology and theoretical physics. Stephen Hawking's proposal that the universe has no boundaries was a revolutionary idea that reshaped the way we think about the cosmos. His no-boundary condition offered a new understanding of the universe's origins, time, and the nature of reality itself. By integrating quantum mechanics with general relativity and proposing a universe without a distinct beginning, Hawking provided a more unified and coherent model of the universe that continues to influence cosmology today. Stephen Hawking's proposal of the no-boundary condition radically transformed the way we approach the concept of the universe's origins and structure. By suggesting that the universe has no boundaries, he did not merely challenge our understanding of the cosmos, he also fundamentally changed the way we think about space, time, and the very fabric of reality itself. This was a direct challenge to classical ideas of the Big Bang, which had suggested that the universe began from a singularity, a point of infinite density and temperature where the laws of physics break down. The classical model painted a picture of the universe's birth as a sharp, well-defined moment in time, a singular event in which time itself began. However, Hawking's work shattered that view by proposing that the universe could have no boundary in time or space, and that the Big Bang was not the beginning in the way traditional models had suggested. The significance of this idea lay in its rejection of the concept of a singularity, which had been at the heart of the Big Bang model. According to traditional cosmology, the universe originated from a singularity, a point where all matter and energy were infinitely compressed. This notion presented severe problems for physicists, particularly because it implied that the laws of physics, including general relativity, could not be applied to such a point. In the singularity, space and time as we understand them broke down, making it impossible to apply conventional physical laws. This presented a paradox. If the universe began as a singularity, what was the cause of this event? What happened before the Big Bang? And how could time itself have a beginning? Hawking's radical departure from this view came when he introduced the idea of imaginary time. Imaginary time, a concept borrowed from the realm of mathematics, allowed him to view the universe's origin in a completely new way. In the traditional model, time was considered to be a linear progression from past to present to future. This model suggested that the universe had a definite beginning, a clear starting point marked by the Big Bang. However, Hawking's idea of imaginary time suggested that time could be treated as a dimension of space, not as a simple line of progression. This allowed the beginning of the universe to be described as a smooth, boundaryless process, rather than a sudden, sharp moment of creation. By treating time as imaginary, the concept of a singularity was eliminated, and the universe's origin could be described in a way that was consistent with both quantum mechanics and general relativity. The no-boundary condition proposed that the universe did not have a singular point of origin, but instead had a smooth, finite boundary in a higher dimensional space. In this model, the universe could be described as having no sharp edges or boundaries, with the beginning of the universe smoothly transitioning from a quantum state. The application of imaginary time allowed the universe to be seen as a self-contained, finite system, without a singular starting point. Time, in this sense, could be thought of as a curved dimension, which did not require a distinct beginning or end. The universe, in Hawking's vision, was not something that began at a specific moment in time, but was an ongoing process that existed in a smooth, continuous flow. This new perspective had profound philosophical implications. It challenged the very concept of time itself. In traditional cosmology, time was seen as a linear progression that had a clear beginning. The idea that time might have no beginning, or that it might be part of a continuous, self-contained structure, shifted the way we think about the universe and its origins. If time did not have a distinct beginning, then the concept of before the Big Bang became meaningless. In this model, there was no before because time itself was finite and boundaryless. The universe was not created from a singular point, but emerged from a timeless, smooth state that was consistent with the laws of quantum mechanics. This radical view suggested that the universe could have no beginning in the traditional sense, and instead, it could be viewed as a self-contained system that was eternal and cyclical, without the need for a creator or an external cause. The concept of the no-boundary condition also offered a solution to some of the most pressing problems in cosmology. One of the most enduring questions in physics has been the issue of the fine-tuning of the universe. Why is the universe so perfectly suited to life? Why do the constants of nature seem so precisely calibrated to allow for the existence of stars, planets, and life? In traditional cosmology, these questions were difficult to address, as they suggested a universe that was specially designed or created with a specific purpose in mind. Hawking's model, however, offered a natural explanation for these observations. In a boundaryless universe, the fine-tuning of the cosmos could be explained by the idea that multiple universes exist within a larger multiverse, each with different properties and constants. In this view, our universe is just one of many possible universes, and its properties are not the result of a special design, but simply the outcome of quantum processes that lead to different configurations of the universe. This concept of the multiverse, although still speculative, is an important aspect of the no-boundary condition and has led to many new ideas and research directions in modern cosmology. The idea that our universe could be just one of many that exist within a larger multiverse offers a potential explanation for why the constants of nature are finely tuned to support life. It also suggests that the universe's properties may not be as unique or special as we once thought. Instead, our universe may be just one of many, each with its own set of laws and constants, and the particular conditions that allow life to exist are simply the result of the probabilistic nature of quantum events. The no-boundary condition also addressed the issue of determinism in the universe. Before Hawking, the Big Bang theory suggested that the universe began from a singularity and followed a deterministic course governed by the laws of physics. In this view, if we knew the state of the universe at any given time, we could predict its future with absolute certainty. However, Hawking's work proposed that the universe was not deterministic but probabilistic. The early universe, governed by quantum mechanics, was subject to the uncertainty principle, which states that it is impossible to precisely predict the outcome of quantum events. The no-boundary model suggested that the early universe was not a deterministic, predictable process, but a quantum event governed by probabilities. This view allowed for multiple possible outcomes and histories, each one unfolding according to the probabilistic laws of quantum mechanics. Hawking's work also had profound implications for the future of cosmology. His no-boundary condition opened up new possibilities for understanding the evolution of the universe and its ultimate fate. The model suggested that the universe could have always existed in some form, with no need for a definitive beginning. This model also led to new ideas about the ultimate fate of the universe. If the universe had no beginning and no boundary, then perhaps it would continue to evolve indefinitely, following the laws of quantum mechanics and general relativity. Some cosmologists have speculated that the universe could eventually reach a state of equilibrium, in which it continues to expand and evolve without any distinct end. Beyond its scientific implications, the no-boundary condition also raised philosophical questions about the nature of the cosmos. If the universe had no boundaries and no distinct beginning, what did this mean for our understanding of existence? Did the universe have a purpose, or was it simply a natural outcome of quantum processes? Could the universe exist without a creator, or was there some deeper explanation for its existence? These questions remain at the heart of ongoing debates in both cosmology and philosophy. Despite the radical nature of Hawking's ideas, the no-boundary condition has had a profound influence on modern cosmology. His work has inspired a new generation of cosmologists to think about the universe in fundamentally different ways. The idea of a boundaryless universe, governed by the principles of quantum mechanics, has provided a more unified framework for understanding the universe's origin, structure, and evolution. It has also raised important questions about the nature of time, space, and reality itself. Hawking's contributions have not only reshaped our understanding of the cosmos, but also opened up new avenues for scientific exploration and philosophical inquiry. The no-boundary condition is, in many ways, a culmination of Hawking's lifelong quest to understand the deepest questions about the universe. It represents a synthesis of his ideas about quantum mechanics, general relativity, and the nature of time. His work has had a lasting impact on cosmology, inspiring new theories, models, and experiments that continue to shape our understanding of the universe. Whether or not the no-boundary condition will ultimately prove to be the correct model for the universe's origin remains to be seen, but it has undoubtedly changed the way we think about the cosmos and our place within it. Stephen Hawking's vision of a boundaryless universe, governed by the laws of quantum mechanics, will continue to influence the field of cosmology for years to come. Stephen Hawking's groundbreaking work on the nature of black holes and their relationship to the universe's creation and ultimate fate has shaped the field of theoretical physics. One of the most transformative concepts he developed was the idea of black hole radiation, now famously known as Hawking radiation. Before his work, black holes were thought to be regions of space where nothing, not even light, could escape. However, Hawking's 1974 discovery challenged this view, suggesting that black holes could emit radiation due to quantum effects near their event horizons. This was a stunning revelation because it implied that black holes could slowly lose mass and eventually evaporate completely. This finding not only changed our understanding of black holes, but also brought new insights into the fundamental connections between quantum mechanics, general relativity, and thermodynamics. In addition to his work on black holes, Hawking made significant contributions to the field of cosmology, particularly regarding the early universe. One of his most important ideas was his no-boundary condition, which proposed that the universe had no boundaries or singularity at its beginning. This idea rejected the notion that time had a clear starting point, instead suggesting that the universe emerged from a quantum state with no distinct origin. This model was a direct challenge to the traditional Big Bang theory, which had the universe originating from a singularity. By applying the principles of quantum mechanics to the universe's creation, Hawking provided a unified theory that merged the laws of general relativity with quantum mechanics, offering a fresh perspective on the universe's beginning and its infinite, self-contained nature. Another aspect of Hawking's work that revolutionized cosmology was his work on the arrow of time. He delved into the concept of time, particularly the way in which the universe's time is not symmetrical. Time flows in one direction, forward from past to future. Hawking explored why this is the case, proposing that the arrow of time is closely linked to the second law of thermodynamics, which states that entropy disorder in a closed system always increases. He argued that the universe started in a low entropy state, and over time, entropy increased, resulting in the flow of time we experience. This concept tied together thermodynamics, quantum mechanics, and cosmology, providing an explanation for why time seems to flow in one direction rather than being reversible. Hawking's work on the possible existence of multiple universes, or the multiverse theory, was yet another key area of his research. Although not fully accepted by all scientists, Hawking proposed that our universe may be just one of many that exist within a multiverse. This idea was a natural extension of his work on the no-boundary condition, as it suggested that multiple universes could emerge from the same quantum fluctuations, each with its own set of physical laws and constants. The multiverse theory has opened up new avenues of research and debate, challenging traditional ideas about the uniqueness of our universe and suggesting that the cosmos we observe might be just one of countless others. Through these groundbreaking ideas, Stephen Hawking transformed our understanding of the universe, blending deep mathematical insight with speculative ideas that pushed the boundaries of what we thought possible in physics. His contributions continue to influence modern cosmology and quantum physics, providing a framework for future discoveries and offering profound implications for our understanding of time, space, and the fundamental laws of nature. Stephen Hawking's contributions to science transformed our understanding of the universe in profound ways, with his work spanning various areas of theoretical physics and cosmology. One of his most significant breakthroughs was his work on the nature of black holes, particularly his theory that black holes emit radiation, now known as Hawking radiation. This discovery in 1974 challenged the previously accepted idea that nothing, not even light, could escape from a black hole. Hawking's theory suggested that quantum effects near the event horizon, the boundary beyond which nothing can escape, would cause black holes to emit radiation and lose mass over time. This idea bridged quantum mechanics with general relativity, two fields that were once thought to be incompatible, and fundamentally altered our understanding of black holes, their eventual evaporation, and the nature of space and time. Another of Hawking's key contributions was his development of the no-boundary condition, which proposed that the universe had no boundaries or edges. This idea was a radical departure from the traditional Big Bang theory, which posited that the universe had originated from a singularity, a point of infinite density and temperature. Hawking's no-boundary proposal suggested that the universe did not begin at a specific point in time, but instead emerged from a quantum state with no distinct boundary. This work challenged the notion of a beginning to time itself, and suggested that time, as we understand it, could be finite and unbounded, existing in a quantum realm where space and time themselves curved and connected in ways previously unimaginable. Hawking's exploration of the arrow of time was another critical area of his work, where he investigated why time seems to flow in one direction, from the past to the future. According to the second law of thermodynamics, entropy, or disorder, increases in a closed system, and Hawking linked this increase in entropy to the flow of time. He proposed that the early universe was in a low entropy state, and as the universe expanded and evolved, entropy increased, thus giving time a direction. This concept not only tied together quantum mechanics and thermodynamics, but also provided an explanation for the asymmetry of time's flow, further illustrating the relationship between the universe's evolution and the increasing complexity of the cosmos. One of the more speculative but intriguing ideas Hawking developed was his multiverse theory, which suggested that our universe might be just one of many that exist in a larger multiverse. In his work on the no-boundary condition, he proposed that quantum fluctuations could give rise to multiple universes, each with its own unique set of physical laws and constants. While this idea is still debated among cosmologists, it opened up a new realm of possibilities for understanding the nature of reality, suggesting that our universe may not be the only one, and that the laws of physics we observe could be just one version of many. Lastly, Hawking's ability to communicate complex scientific ideas to the public made his work even more influential. His best-selling book, Time's A Brief History of Time, introduced millions of people to concepts in cosmology, quantum mechanics, and general relativity. With his clear writing and engaging style, Hawking brought the mysteries of the universe into the homes and minds of everyday readers, sparking a global interest in the nature of the cosmos and the science behind its origins. His efforts to make science accessible to a broad audience were an essential part of his legacy, ensuring that his groundbreaking work would continue to inspire generations of scientists and laypeople alike. Stephen Hawking's work left an indelible mark on the scientific community and the way we understand the universe. From black holes to the multiverse, his ideas continue to challenge existing theories, inspire new research, and provoke deep questions about the nature of time, space, and existence itself. Stephen Hawking's work in cosmology and theoretical physics redefined how we understand the universe. His contributions spanned a range of complex and deeply philosophical ideas that not only advanced scientific knowledge, but also altered the course of research in fundamental physics. One of his most notable achievements was his theory of black hole radiation, now known as Hawking radiation. Before this groundbreaking idea, black holes were thought to be completely inert regions of space where not even light could escape. However, Hawking proposed that due to quantum effects near the event horizon, black holes could actually emit radiation and lose mass over time, eventually leading to their evaporation. This discovery combined elements of quantum mechanics, general relativity, and thermodynamics in a way that had never been done before, revolutionizing our understanding of black holes and providing a bridge between two fundamental yet previously incompatible theories. Another important aspect of Hawking's work was his formulation of the no-boundary condition for the universe. In contrast to the classical Big Bang model, which suggested that the universe had a definite beginning, Hawking's theory proposed that the universe did not have a singular starting point or edge. Instead, he suggested that the universe could be described by a smooth, boundaryless geometry, a concept drawn from his work on quantum cosmology. In this model, time itself becomes finite, but without a distinct beginning, as the universe evolved naturally from a quantum state. The no-boundary condition proposed that, just like the surface of a sphere, the universe may be finite in size, but without any edges or boundaries, eliminating the need for a creator or external cause for its existence. Hawking's work on the arrow of time also made significant contributions to the understanding of time and its flow. The arrow of time refers to the one-way direction in which time flows, from the past to the future. This concept, which had puzzled scientists and philosophers for centuries, was explained by Hawking in the context of the second law of thermodynamics. He proposed that the increase in entropy, or disorder, in the universe over time explains why time moves in a single direction. In the early universe, the entropy was low, but as time progressed and the universe expanded, entropy increased, leading to the flow of time we experience. This idea not only explained the asymmetry of time's flow, but also connected cosmology with thermodynamics in a new way, bridging the gap between the microscopic world of particles and the macroscopic structure of the cosmos. Hawking's speculation about the multiverse, or the idea that there are many universes beyond our own, expanded the possibilities of cosmological theory. His work on the no-boundary condition suggested that the universe we observe could be just one of many that exist within a larger multiverse. This theory proposed that quantum fluctuations could create multiple, parallel universes, each with different physical constants and laws. While this idea remains highly speculative and is not universally accepted, it has influenced many cosmologists and has been a subject of growing interest in modern physics. The multiverse theory challenges the uniqueness of our universe, suggesting that the cosmos we know could simply be one possibility in a vast, infinite landscape of universes. Another important area of Hawking's work was his exploration of the nature of singularities, particularly those that exist at the center of black holes. In his famous collaboration with Roger Penrose, Hawking developed the Penrose-Hawking singularity theorems, which showed that singularities are a natural consequence of general relativity. These theorems proved that under certain conditions, space-time must collapse into a singularity where the laws of physics as we know them break down. This work had profound implications for understanding the structure of space-time and the limitations of our current theories. Hawking's exploration of singularities led to important questions about the nature of space, time, and the fundamental forces that govern the universe. Hawking's ability to make complex scientific concepts accessible to the public was also a crucial part of his legacy. His best-selling book, Times, A Brief History of Time, brought complex ideas in cosmology and physics to a general audience, sparking widespread interest in science. The book discussed the nature of the universe, the Big Bang, black holes, and the nature of time in terms that were understandable to non-scientists. Hawking's ability to communicate science to the public helped to make advanced theoretical physics more approachable, inspiring a new generation of scientists and thinkers. Stephen Hawking's work has had a lasting impact on the fields of cosmology, quantum mechanics, and general relativity. His insights into black hole radiation, the structure of the universe, the flow of time, and the nature of singularities have reshaped modern physics. Moreover, his ideas about the multiverse and the infinite possibilities of the cosmos have opened up new avenues for scientific exploration. Through his groundbreaking work and his efforts to make science accessible to everyone, Stephen Hawking has left a legacy that continues to inspire and challenge our understanding of the universe. Stephen Hawking's work revolutionized our understanding of the universe and its most fundamental laws. One of the key areas where his contributions had an immense impact was in the realm of black holes. Traditionally, black holes were thought to be regions of space where gravity was so strong that nothing, not even light, could escape. This view had long been accepted, but Hawking introduced a radical new idea that changed the way scientists thought about these mysterious objects. In 1974, he proposed that black holes actually emit radiation due to quantum effects near their event horizon, the boundary beyond which nothing can escape. This concept, known as Hawking radiation, suggested that black holes are not entirely black, but instead slowly lose mass over time as they emit radiation. This was a groundbreaking discovery because it bridged the gap between quantum mechanics and general relativity, two pillars of modern physics that had been thought to be incompatible. The idea of black holes emitting radiation had profound implications for our understanding of the nature of space and time. Another revolutionary aspect of Hawking's work was his theory of the origin of the universe. He developed the no boundary condition, which proposed that the universe did not have a singular, defined beginning, but instead emerged smoothly from a quantum state, without any boundary or edge. This idea stood in direct contrast to the traditional Big Bang model, which suggested that the universe began from a singularity, a point of infinite density and temperature. Hawking's no-boundary theory, in combination with his work on quantum cosmology, suggested that the universe could be finite but without any boundaries, much like the surface of a sphere. This model proposed that time itself could have no beginning or end, challenging the classical idea that time started with the Big Bang and providing a new way of thinking about the origin of the universe. Hawking's exploration of the arrow of time also made a significant contribution to our understanding of the flow of time. Time, as we experience it, seems to flow in one direction from past to present to future. Hawking linked this one-way flow of time to the second law of thermodynamics, which states that in a closed system, entropy, disorder, always increases over time. He suggested that the universe began in a low entropy state, which is why time flows in one direction. As the universe expanded, entropy increased, giving rise to the arrow of time. This connection between time's direction and the increase in entropy helped explain why time seems to move only forward, providing insight into the relationship between thermodynamics and the evolution of the universe. In addition to his work on black holes and the nature of time, Hawking also made significant contributions to the concept of the multiverse. The idea of a multiverse, multiple, potentially infinite universes existing alongside our own, was a natural extension of his work on the no-boundary condition. In this framework, Hawking proposed that quantum fluctuations could give rise to different universes, each with its own set of physical laws and constants. This idea offered a potential explanation for why our universe is so finely tuned for life. If there are multiple universes with varying properties, it could simply be that we happen to live in one where the conditions are just right for life to exist. The concept of the multiverse has since become a topic of much debate and research in cosmology, challenging the traditional notion that our universe is unique. Hawking also explored the nature of singularities, particularly the one at the center of black holes. A singularity, according to general relativity, is a point where the gravitational field is so intense that space-time curves infinitely and the laws of physics cease to function. Hawking, in collaboration with Roger Penrose, developed the Penrose-Hawking singularity theorems, which showed that singularities are not just theoretical anomalies, but are likely to exist in the real universe under certain conditions. These theorems demonstrated that singularities are an inevitable consequence of general relativity and provided important insights into the structure of spacetime, the nature of gravity, and the limits of our current theories. In addition to his scientific discoveries, Hawking became a global figure known for his ability to communicate complex scientific ideas to the public. His best-selling book, Time's A Brief History of Time, Times introduced millions of people to the mysteries of cosmology, black holes, and the nature of the universe. Through his writing and public lectures, Hawking brought the wonders of modern physics into the mainstream, making the study of the universe accessible to a broader audience. His ability to explain deep, abstract concepts in clear and engaging terms helped popularize science and inspired countless individuals to explore the mysteries of the cosmos. Finally, Stephen Hawking's legacy is also defined by his determination and resilience in the face of a debilitating illness. Diagnosed with ALS amyotrophic lateral sclerosis at the age of 21, Hawking was given only a few years to live. Despite his physical limitations, which left him almost completely paralyzed and dependent on a speech-generating device to communicate, he continued his groundbreaking work in theoretical physics. His personal story of perseverance and triumph over adversity made him an icon not only in the scientific community, but also in popular culture, demonstrating the power of the human spirit to overcome even the most formidable challenges. Stephen Hawking's work has left an indelible mark on the field of cosmology and beyond. His insights into black holes, the origins of the universe, the nature of time, and the concept of the multiverse have reshaped the way we understand the cosmos. Through his work, Hawking bridged the gap between quantum mechanics and general relativity, offering a unified vision of the universe that continues to inspire scientists and thinkers worldwide. His ability to communicate complex, scientific ideas to the public has made him one of the most influential figures in the history of science. And his personal story of overcoming physical challenges to continue his work serves as a powerful reminder of the resilience of the human spirit. Hawking's contributions will continue to shape our understanding of the universe for generations to come.